Hi, my name is Darin Knaus. I'm from Creare, and I'll be talking today about an engine particle ingestion classifier for gas turbine engines. We call this technology EPIC, or the EPIC sensor, and it's a sensor for measuring sand and dust ingestion and loading in gas turbine engines. It's intended to warn pilots and air crews about threats to their aircraft due to excessive sand and dust ingestion, and can also be used for planning maintenance. And research purposes as well. Our project is the result of a Navy STTR program from Office of Naval Research. Our technical monitor is Steve Martins from ONR. My Creare collaborators are Veronique Archambault-Leger and Paul Mavizzo from Creare, and also Professor Thomas Cahill from Arizona State University. Creare is an engineering research and development firm located in Hanover, New Hampshire. Creare means to create, and we create value for our clients by solving their most difficult problems through technology innovation. Creare is known for transitioning technologies to key products or programs, and some examples are shown on this slide. On the top left is a cryocooler that was developed at Creare and installed on the Hubble Space Telescope in flight. This solved a thermal management problem or issue that was encountered on the Hubble Space Telescope, and is an example of a Creare product that we would develop. This would typically be a high-value, low-volume product like a cryocooler for a telescope. Creare has licensed cryogenic machining technology to companies like MAG Industries. And we've also recently developed non-contact metrology technology relevant to the F-35 Joint Strike Fighter program. And also a recent transition was the compact swaging machine, which is a machine used to attach terminals to cables used for launch and recovery operation on aircraft carriers. Creare's core expertise is thermal and fluid engineering. We are known for hardware, both hardware and software development, and have done a lot of work related to fabrication and manufacturing processes. Our customers include the federal government, including all branches of the military, NASA, DOE, and NIH. We work for a variety of large and small industrial companies, both domestic and international. Particle ingestion is important in gas turbine engines, especially in engines used for low altitude aviation applications. This would include aircraft like helicopters or tilt rotor aircraft. Particle ingestion impacts engine maintenance and intervals, the durability and lifetime of an engine. It impacts the logistics associated with engine ownership and operation and the total cost of ownership of these systems. The clogging can impact cycle performance by degrading the engine or by imposing requirements for filtration or particle separation on the cycle. And in extreme cases, particle ingestion can actually lead to engine failure during flight and crash of the aircraft. Our goal is to develop a new flight sensor for detection and classification of ingested particles. The purpose is to provide early warning when there's an acute risk to the aircraft due to particle ingestion, and also provide data in a cumulative fashion over time for maintenance planning. And shown on this slide are two examples of aircraft where this technology would be applicable. The Black Hawk variants that use the GE T700 engine, and also the V-22 is an aircraft that often operates in dirty environments. Gas turbine engines are susceptible to clogging because there are many narrow flow passages and channels inside a gas turbine engine. Notable are cooling holes that are found in combustion liners and turbine blades. In addition to just physical blockage due to the presence of particles, there's a problem known as the CMass problem. And CMass is an acronym that stands for calcium, magnesium, aluminosilicate. And these are components, elemental components that are commonly found in sand and dust that are ingested into engines. And CMass refers to components that have low melting temperature relative to silica, which is sand and has a high melting temperature. Historically, the operating temperature of gas turbine engines has increased over time as improvements have been made in cooling and the materials that are used in the engine. And that's shown in the table shown at the bottom of the slide. The x-axis here is the year, and the y-axis is turbine temperature. And you can see that there have been certain jumps in performance related to things like film cooling and cooling strategies in turbines, the emergence of thermal barrier coatings, and the emergence of ceramic matrix composite materials. And what has happened is as the turbine temperature has increased, it has allowed these CMass components to melt in the engine or in the turbine. And that causes a further problem beyond the normal physical solid phase clogging problem, where the particles can melt and they can glass or flow in the engine and further exacerbate clogging. And this is a verified operational risk. There have been some notable incidents in the news, particularly a crash of a V-22 at Bellows Air Force Base that was related to sand and dust ingestion. So this is a known verified issue that can acutely affect the safety of aircraft. That brings us to our sensor technology. We call our sensor EPIC. It stands for Engine Particle Ingestion Classifier. EPIC is a suite of sensors, including different types of sensors that have different functionality and purpose. One sensor is an optical sensor that measures particle size and load. So these are two of the physical properties that you would want to know about the sand and dust that's being ingested in the engine. This is the easier measurement to make relative to the composition measurement, which I'll talk about next. Optical sensors are laser-based. They tend to have very low size, weight, and power. So they're well suited for integrating with engines. And the sensor that we're using is derived from a sensor from a company called Measurement Science Enterprise, MSE, and they call it a micro-V. The micro-V it involves two laser sheets that are projected into the flow, and two sensors that record light scattered from the laser sheets as particles transit them. The sheets are separated by a known distance. So in addition to counting particles as they go by and interact with the sheets, you can get velocity information from the micro-V. And this sensor was actually developed for velocimetry applications in fluid dynamics. Particle size is inferred by the scattering signal as well. So we get three pieces of information from the optical measurement: count, size, and velocity. And again, this is relatively low size, weight, and power. The other part of our system is our main innovation that we're trying to apply to this problem, which is to use X-ray fluorescence to classify the particles. So here we're not measuring the physical properties of the particles. We're trying to measure their composition as it relates to their chemistry and properties such as melting temperature. XRF uses X-rays to fluoresce elements, and material will have a signal that's a spectrum that is a fingerprint that shows the elemental composition of that material. And one of those spectrum is shown in the bottom right of the slide. X-ray fluorescence devices can be relatively compact. Handheld XRF is shown in the bottom left of the slide, and these are often used for things like lead paint screening. X-ray fluorescence has low size, weight, and power relative to other technologies that you might use to classify the particles, and one example would be a mass spectrometer. This slide talks about the current status of our program. Previously, we demonstrated particle size, loading, and classification in a laboratory environment using laboratory sensors. So we used commercial off-the-shelf X-ray fluorescence sensors and the standard configuration of the MSE Micro V for optical counting and sizing. What we're currently working towards is developing a flight or a flight-like version of the technology. So we've developed a custom XRF that has low size, weight, and power and is optimized for the dusts that are of interest to the current application. We've also developed a flight version of the optical sensor that is configured a little bit differently than the commercial sensor. And we've developed a number of integration components such as windows, optical windows, and concentrators that can be used with the sensors and configured for different applications. The purpose of our current project, which is a Navy STTR Phase 2, is to validate the flight versions of our sensors on a high-fidelity rig test, which will be performed at GE at their Lynn, Mass facility. This slide speaks to the benefits and advantages of our technology. First and foremost, we're trying to provide a real-time flight capability for measuring particles ingested in engines. This is a new capability. Currently, the aviators, military aviators, have no feedback on sand and dust ingestion, other than if there was a significant performance shift to the engine or their visual acuity and observation of the conditions outside the aircraft, for example, if they're flying in a brownout. So at its core, we're trying to provide a new capability that will provide information to help pilots understand the risk to their aircraft. Our technology involves a new way of classifying the particles. So in addition to just telling you the amount and the size of the particles, we're going to provide information on the composition of the particles. And this is important for things like understanding whether you're ingesting CMass particles that could have low melting temperature and could have elevated risk relative to higher melting temperature particles. And the way that we do this will be by providing these XRF fingerprints and analyzing those data to determine whether a dust is a good or a bad dust. Our approach provides capability in the most compact and lightweight footprint that we can provide. The optical sensor is inherently compact, and the XRF sensor is larger and has higher swap, but it is reasonable in its swap trade relative to technologies like mass spec. We would also like to point out that this technology could also be used in research and development aircraft or for ground testing. And you wouldn't necessarily have to configure a flight version for an operational aircraft in the same way that you would for research and development purposes, where you might locate more sensors around the aircraft to collect higher volume of data. Finally, the technology can be used to collect cumulative data on the health status of an engine over time. This will allow maintainers to plan maintenance based on actual loading and not on conservative schedules, and can also be used as a data input for things like digital virtual twin models of engines to track engine status and degradation over time. The slide talks about transition of the EPIC technology to the end user, which is, our initial end user will be naval aviation. Our current project is focused on integration hardware and a sensor rig demonstration. That project is slated to end Q1 of 2022, and we're in the thick of that work currently as we speak. Subsequent to our STTR, there is an option component that would involve an engine test. And our plan is to apply the sensors in a T700 engine at NavAir that's used as part of the EaseMet program to demonstrate the sensors on an actual engine. So that would occur on a STTR option. Beyond the STTR program, we would need to work to certify the EPIC technology for flight. moving towards a demonstration on an aircraft. This would most likely be a rotary wing aircraft, and we're projecting that would occur in the 2025 timeframe, and actual transition would occur in the 2025 to 2026 timeframe. The primary transition advocates for this would be the multi-mission helicopters program, H-60, which uses the T-700 engines. Would also be interested in engines like the ITEP engine. And also the V-22 Joint Program Office has significant interest in technologies for sand and dust ingestion. This slide talks about market analysis and where we're hoping to apply the EPIC technology. We're initially targeting Navy helicopters like the SH-60 Seahawk. Sand and dust ingestion mostly impacts aircraft operating at low altitude where sand and dust can be ingested. So we're mostly talking about helicopters and rotary wing aircraft. Our initial work has focused on transition to the T-700 engine, which is a legacy engine that has a particle separator that works well for integration of sensor technologies. Other Navy applications include the V-22 Osprey, the ship-to-shore connector, which is a vehicle that often operates in dusty environments, and it's a ground and sea vehicle that has gas turbine power. And it could also be applied to Navy aircraft that are fixed-wing aircraft running turbofan engines like the F-18 and F-35. The F-35 has a vertical takeoff mode and can operate in dusty or sea spray environments. And the F-18 can also operate in sea spray or polluted environments. Other DoD applications include all the rotary wing aircraft throughout the military. Fixed wing aircraft would include transports like the C-17 Globemaster that's used in the Air Force, and also ground vehicles that use gas turbine propulsion like the M1 Abrams tank. And then the commercial applications primarily have to do with commercial aviation. These would generally be turbofan engines, and some notable applications would be to aid in operations near volcano plumes or operations in polluted airspaces to measure and understand the composition of those airspaces, especially for research. Our approach for transitioning this technology is to transition the optical sensor through our partners at Measurement Science Enterprise, and to separately transition the X-ray fluorescence sensor either by licensing to an existing X-ray vendor, such as Proto Manufacturing, whom we've worked with to develop the custom XRF, or a company like our sister company, Darin. Darin is a Creare affiliate. They work on low-rate initial production of highly engineered products, and we've successfully used this model for other technologies like the Creare compact swaging machine that was licensed and assembled at Darin. That concludes my presentation. If you'd like to learn more about Creare or the EPIC technology, feel free to call me or email me or visit our virtual booth. Thank you for your time and attention during this unusual virtual presentation, and I appreciate your interest.